Okay, let's talk about related rates problems. This will be our first excursion back into more specifics of how to use, well, in this case, derivatives, and in other videos, integrals. So a related rates problem usually has a relationship between two quantities, and those two quantities are changing in some related manner, and that relation is usually given by an equation, and we want to know how fast one quantity changes with respect to the other. And derivatives are all about rates, so we use derivatives to do this. So let me just review rates a little bit. And a rate, first sort of thing I want to mention is it's a ratio, right? It's a ratio between two quantities. Usually the denominator quantity is some measurement of time. But that doesn't have to be true, right? Like if you go to the gas station, you can buy a vehicle full of gas, and the rate at which you have to purchase gas is usually in dollars per gallon. That's an example of a rate. Miles per hour, lots of rates out there. They don't always have to deal with time, but a lot of the calculus problems you'll see in a text are usually dealing with time as the denominator quantity. Okay, so let's just do a simple one here. So example, we have a spherical snowball, and it is melting at the rate 1 cubic foot cubic per hour. If it always remains a sphere, what rate in square feet per hour is the surface area changing? Okay, so we know the rate of the volume. We want to know the rate of the surface area. So somehow I'm going to have to relate volume to surface area. Okay, so we might recall that we've got a relationship between radius and volume, as the volume as a function of r is equal to 4/3 pi r cubed. And you also might recall that the surface area as a function of r is equal to 4 pi r squared. Okay, neither of these have the relationship with hours built into them. These are sort of physical constraints. They're a volume and a radius. They're dimensional equations. A surface area, so an area, and a radius. They relate a length to a volume and a length to a surface area, but we have to include time somehow. Okay, so I need this relationship between volume and surface area, and right now it's sort of not a very good relationship because I've got two different equations here. But that's okay, we can work with that. I could solve one equation for r and get r equals something in terms of the surface area, and then plug that into the volume equation. I could have a equation that relates volume to surface area directly. Or we'll see that we can leave them like this and sort of do a two-step relationship problem. Take the volume, how fast it's changing with respect to how fast the radius is changing, and then use that radius changing in the surface area equation to figure out how fast the surface area is changing. And that's going to be our process. But I still have to get this time variable included. So I kind of have to think about what's happening. The volume is changing with time, and so the radius is also changing with time. I should be thinking of these things as a function of time rather than a function of the radius. And so I can do that by just saying, well, the volume is a function of the radius, which is a function of time, and I can just write that that's equal to the radius as a function of time cubed. And this still holds. The radius is just changing with respect to time here, but when I plug the radius at certain times into the volume function, I get the volume at those times as well. So now I have a function of volume with respect to time is equal to some function of the radius with respect to time. I can do the same thing with the surface area. The surface area at a certain time is equal to 4 times pi times the radius at that specific time squared. Use square brackets here, I guess. Okay. And now I've got relationships between volume and time and the radius, and surface area and time and the radius. Okay. So let's differentiate these things. I'll get that dv dt, which is the initial rate of volume per hour. This is dv dt. I'll put that in red. Okay, and this is d surface area. dt is what we want. So taking the derivative of this volume equation with respect to time looks like it's a good start for us. And if I take the derivative of the right hand side with respect to time, I get these constants, 4/3 pi. And I have to use the chain rule on this. It's 3 times r of t, now squared, but times dr dt, the derivative of that radius function. Okay, and I can do the same thing with the surface area function. So I get that dv dsa dt is equal to 4 pi times 2 times r of t times dr dt. Okay, so this helps us relate these two quantities, dv dt and dsa dt. And let's see how we can do that. So let's look at this piece right here real quick. So those 3's are going to cancel, and I get 4 pi r squared, which is exactly the surface area with respect to time, right? So I get that dv dt is equal to the surface area at a specific time times the derivative of the radius with respect to time. And that way I can get that dr dt is equal to 1 over the surface area at a specific time times dv dt. Right? And now I can replace this into my surface area equation. So dsa dt is equal to 8 pi times the radius at a certain time divided by the surface area at a certain time times dv dt. Okay. Let's simplify that a little bit more and get it all in terms of radius. So d surface area dt is 8 pi r of t, that's 8, divided by 4 pi r squared at t times dv dt. And a lot of this cancels. That cancels with one of those. I get a 2. So this is 2 over r of t times dv dt. So the change in the surface area at a specific time is equal to 2 divided by the radius at that time times, well, the volume was 1 foot cubed per hour. 2 has no units on it, radius has no units on it, so this will, well, radius has feet units on it, so this will, as it should, give us a feet squared per hour, as long as I know what the radius is at a certain time. So ds dt is equal to 2 over r feet squared per hour. So the rate of change of the surface area at a specific time depends on the radius at that time. We didn't specify what the radius was, but we could specify whichever radius value we wanted and then figure out how fast the surface area is changing at that specific time. Okay, so let's do another one. And let's say we have sort of a common one in a lot of calc books is a ladder hanging on a wall, and for some reason the bottom is sliding out and we want to know how fast the top is falling down the wall. Right? Okay, so let's say that this is a ladder and it's at an angle of theta. This will be the height of some theta, and this will be the length of theta would be this distance, and the height is this distance. Now, the height and length are related, especially to theta. Let's say the length of the ladder, it's a 20-foot ladder. Okay. So there's kind of our setup. Let's say the problem states we have a 20-foot ladder. The bottom is sliding away from the wall at let's just say 1 foot per second. How fast is the top sliding down the wall when the bottom is, let's say, 7 feet from the wall. Okay, so I have a rate that is one of the quantities that we want to relate, and I have a specific value of one of the quantities that I want to relate. So in the first example, we didn't have a specific value, and that led us just to some relationship equation, right? The relationship equation we had was this. If I had a specific value for the radius, I could have found the exact value for the rate of change at that point in time. Okay, so now I have a specific point in time in mind that I want to find the rate of change at that specific point in time. Okay, I still get to set up a relationship between the height and the length, and that height and length relationship is going to be h of, well, I don't really even need theta in this because I need h of t. So let's not even put theta in this. Let's make this h of t and the length at time t, because I want these with respect to a time variable. I could put it with respect to the angle variable, but let's do it with respect to the time variable. And I get h of t squared plus L of t squared equals, well, 20 squared, or 400. That's going to be the relationship between the height and the length. Okay, so I've got this equation. It's with respect to time already, so I can differentiate with respect to time and get my feet per second if I'd like to. So let's do that. Let's differentiate both sides of this with respect to time. It's kind of an implicit differentiation thing. I'm going to use the chain rule. I've got 2 h of t dh dt plus 2 L of t dl dt equals 0. Oh, so I can divide by 2 on both sides and get h of t dh dt plus L of t dl dt equals 0. Okay, so now what do I do? Well, I know dl dt from the setup is 1 foot per second. I know the length that I want to evaluate at is 7 feet. And in this, that means I can get these two things figured out, but I'd still have to figure out what the height is. However, because I know what the length is, this equation is going to tell me what the height is. Right? If the length at t equals 7 feet, then h of t is equal to the square root of 400 minus 49 equals the square root of 351, which I don't think's a perfect square. Is that 19? No. Anyway, we get the square root of 351, which it is divisible by 3, so it can't be the square root of 19, or it can't be 19 squared. So what is that? 17 times 3. That's also divisible by 3, so that's 39 times 9, which is going to be 3 times the square root of 39. 19 and 3 would be the other two, or 13 and 3. That's not going to go any further. So this is h of t. So I get 3 square root of 39 times dh dt plus 7 times 1 is equal to 0. that tells me dH dt is equal to 7 over 3 square roots of 39 with a negative sign. So it's falling down the ladder at this many feet per second. Or it's falling down the wall at this many feet per second. Okay, so related rates problems sort of have a couple steps to them. We've got to find the relationship between quantities that are the numerator of the rates that we need to compare. Okay, so let's review. That was the volume with respect to time. We wanted dV dt and ds a dt in the first one, so this is kind of an aside. Because we wanted to compare these two rates, we needed a relation between volume and surface area. Okay, and in the second problem, we needed a relationship between dH dt and dL dt. So we needed an equation relating height and length. Okay, so that's kind of the first step. The second step is write the relation as a function of the denominator variable, the denominator quantity. Okay, so we had time as our denominators in both of them, so we had to write the functions as functions of time, like h of t squared and then L of t squared. Add those together and you get 400. That was our function as a relation of time. And then 3, differentiate using the chain rule. We usually have to use the chain rule because, well, when we get these relationships, we've written them as functions of time, so the relationship is an equation in the variables that we've now made functions. So we're going to have to use product rules, chain rules, that sort of thing to differentiate them. It's almost like implicit differentiation again. And then 4, we just plug in values or solve for the ratio that we want. By evaluating or simplifying at the specific values that the question calls for. Okay, so that's kind of your standard related rates problem. It's an application in finding a relationship between variables and then applying a derivative and simplifying, solving for what you need.